students, welcome to the Swayam course Microbial Technology. I am Dr. Richa Sahu, working as an assistant professor at University Teaching Department, Chhattisgarh Swami Vivekanand Technical University. So today we'll be talking about microbial growth kinetics, and in the previous lecture you learned about the microbial growth curve. So what are the objectives of this particular lecture? We will understand the concept of microbial growth again. We will revise the differentiation between bacterial cell growth and bacterial replication. We will be revising a little bit about bacterial population growth curve in a batch culture, and we will be talking about description of what is happening to the bacterial cell at each stage of batch cell cycle. And finally, we will be talking about the growth kinetics of each stage of growth curve mathematically. So let's talk about the growth of microorganism. Let's revise a little bit about the growth of microorganism. So growth in microorganism is basically increase in the number of bacterial cells rather than the increase in the size of individual bacteria. So this is the basic difference between the growth in bacteria and in eukaryote like us. For us, the growth is the increase in size as well as increase in the weight. But in the case of microorganism, growth is increase in the number of the microbial cells, not the increase in size and individual bacteria. So bacterial species only maintained if the population continues to grow. If you want to maintain the bacterial species, they need to grow continuously and they need to increase their population. Bacterial division is majorly binary fission. The most common method of reproduction, it's a type of asexual reproduction where the parent cell split into two daughter cells. Here in the image you can see one parent cell, and via binary fission DNA replication happens, then the cytoplasm divides, and finally one mother parent or the one bacterial cell give rise to two daughter cells. These all things we have talked about in growth curve. I am just revising before going directly into mathematical expression of every stages of the growth curve. So how the bacterial cell divide, or what kind of growth do you see in bacteria? So basically you see logarithmic or exponential growth in the microorganism or bacteria. What does it mean? The population of bacterial cells divide at a constant rate so that the total number of cells doubles with each division. Means one bacterial cell will give rise to two bacterial cells, and the two bacterial cell will give rise to four bacterial cells, and so on. This is known as exponential or logarithmic growth or in the bacteria. So let's talk about microbial growth. How do you calculate the population size? The population growth is exponential, as I told you in the previous slide. That means 2 will give rise to 4, 4 will give rise to 8, and so on. So population size can be calculated by the expression Nt is equals to N naught into 2 raised to power n. What is Nt? Nt is the final number of cells, N naught is the original number of cells in the culture. Small n is the number of division the bacteria is taking place, the bacteria is doing. Now let's take the example. Why this expression is important? Because you need to understand in the upcoming slide we'll be talking about the kinetics or the mathematical expressions of the growth. So this expression need to be remembered. Let's take an example. If the N naught is 10, the initial number of cells in a cell culture, if for example is 10, it is dividing number of times small n is 12. So after 4 hours, assuming 20 minutes is the generation time, and following the expression you can say the final number of bacterial cell after the time t, which is let's say 4 hours, 40,960 cell will be there. So what is generation time? The mean generation time or the doubling time is the amount of time required for the concentration of cells to double during the logarithmic stage or the exponential stage. It is expressed in the units of minutes. So the growth rate per minute is inversion of mean generation time. That means if the growth rate is high, the generation time would be less. If the growth rate is slow, the mean generation time would be higher. Let's take an example of few microorganisms and the generation time. Escherichia coli is the very common microorganism that you find in a human gut and in the gut of many eukaryotic organisms. So the generation time is 20 minutes. The generation time for Mycobacterium tuberculosis, which causes tuberculosis in humans, is 18 hours. It takes 18 hours to double the population. Same is Mycobacterium leprae, which causes leprosy in humans. The generation time is 14 days. What does it mean? Why do we need to study the growth curve and growth kinetics of the microorganism? Why do we need to know the generation time of the microorganism? So that these microorganisms with a pathogenic is nature, if we know the generation time, we can manage the disease, we can treat the diseases caused by these pathogenic microorganisms. We can design the antibiotic according to the generation time or doubling time. So that is why we are studying growth curve and growth kinetics in this particular course. Now, how do you measure the bacterial growth? Because if we are talking about growth kinetics and growth curve, that means we need mathematical expression, we need the data. How do you measure the bacterial growth? In the previous lecture, we talked about two methods of measuring the growth of the bacteria. One was the direct method where you calculate the individual cells either in terms of turbidity or either in terms of viable cells. The second method is indirect method, which measures the effects of bacterial growth in terms of metabolic activity. Alright, but in case of measuring the growth curve, in case of doing the growth kinetics, we need the direct method because we need to know the individual viable cells or individual cells either in terms of OD or turbidity or either in terms of number of viable cells. So this is the method of direct cell measurement where you serially dilute the cells first, and then you inoculate it, and then after regular interval of time you calculate the number of viable cell by plating. This is known as plating method. You, after every regular interval of time for the growth curve, you take some amount of cell from the batch and then you plate it, and you calculate the number of viable cells in the plate, as you can see in this particular image, and this is the direct method of calculating the bacterial growth. Here is the hemocytometer. You can also use this to calculate the number of cells. You can even calculate, use the spectrophotometer or turbidometer. You can calculate the turbidity of the cells, means you can relate the growth of the cells through turbidity. More turbid, that means more growth. You can either take the OD of that is calculated in the spectrophotometer and you can plot this OD with respect to time to take the growth, to find out the growth curve. So here you can see the standard growth curve of the bacterial cell growth. It is plotted on the x-axis. You can see the logarithmic number of viable cells, number of cells that are there in the culture, and in the on the x-axis you can see the number of hours the growth was taken. So it basically has 4 phases, as you can see, and we have talked about it in the previous lecture as well. The only thing is we will be talking about the mathematical expression and the kinetics in detail in this particular lecture. So the standard growth curve has 4 phases. It starts with the lag phase, where the overall growth of the microorganism is less, and then eventually gets into the high growth phase, or known as exponential growth phase or log phase. The growth of the microorganism in this particular phase is highest, and then it progresses to the third phase of the growth curve, that is the stationary phase, where the net growth becomes stationary. The number of cells that are dividing, or live cells, becomes equal to the number of dead cells. So the overall net growth becomes 0. That is why you can see the straight line, the stationary phase. And finally, the fourth phase of growth phase is the death phase, where the net growth is very much less than the death that is happening in the bacterial cell. Here you can see the growth phases in detail, where y-axis you have the log viable cells per ml and in the time. How you can see two types of line. One is the black line and one is the dotted line. If you talk about the black line, it is taking the viable count. What do you understand by viable count? In the bacterial broth, number of cells is actually live. कितने जिंदा cells हैं उसमें? Because when you calculate the OD or the turbidity or the optical density, it just calculates the turbidity. So when you are talking about the turbid cell or the turbid broth, it takes into account both viable cells and dead cells. So you can plot the growth curve 2 ways. If you are taking into account the viable count, it will look like the black line as you can see in this image. It starts with the lag phase, then the exponential phase. You can see the straight line, the stationary phase, and then the declined death phase. But in case of when you take into account the turbidity or the OD, optical density, you can see it starts with the lag phase, it goes to the exponential phase, and the stationary phase and death phase are same. Why? Because it is taking into account the overall cells that are there in the broth, where you have the viable cells as well as the dead cells. So both ways you can plot the growth curve, they are correct. If you're taking the optical density, it will look like the dotted line as you can see in this particular image. And if you're taking the log of viable cells, the cells which are live, you can see this the growth curve will look like the black one. Both are correct. In microbiology, both are used. As we talked about the four phases, let's start each phase one by one. I will tell you a little bit about the growth curve first. We'll revise the growth curve because we cannot study the kinetics without revising what happens in that particular phase of growth curve. Okay, so let's start with the lag phase, the first phase of growth curve. When the microorganisms that are inoculated in the fresh medium, they do not start the growth immediately. Obviously, when you go into the new environment, being humans also, when you go into the new environment, you take time to adjust there, right? You need to adjust in the temperature that you are living, you need to adjust in the environment that you are living, you need to adjust in the food that are being served to you, right? So in a similar way, the bacteria, when they are inoculated into fresh media or the fresh food that is given to them, they need time to adjust, all right? Though they do not start to grow immediately. The length of the lag phase, how long is the lag phase? That means the adjusting phase of the bacteria in that particular new medium. The length of the lag phase is variable and it depends on the history of the culture and the growth condition that you are giving. The exponentially growing culture inoculated into the same medium. Like for example, if you are using the same medium where the cells were actually existing, initially existing, the lag phase would be shorter. If you are using the same medium, the same growth condition, there would be no lag phase. There would be no lag phase. You will, after some time, you will immediately see the exponential phase. But if you are using an old culture, even if the same media conditions are used, even if the same growth conditions are used, the lag phase will be prolonged because the cells will need to adjust and the cell will need time to replenish themselves. Okay, so the essential constituents to start the growth and cell division, they need to make that. They will be utilizing the growth medium even if it was same, but because the culture was old, they need to replenish them. Okay, they need to make their own food, they need to make the important constituents to start the growth and to start the cell cycle. If the cells are damaged either by heat or by radiation or by toxic chemicals, lag phase of such cells are very prolonged because they need to repair the cell first. They will be repairing the cell first and they will replenish themselves and then they start growing and dividing. The cells transferred from a rich medium to a poor medium, again the lag phase will be prolonged. Similarly, because they need to synthesize more enzyme, they need to synthesize more machinery to enable them to, for the synthesis of the macromolecule they need to have for the initiation of the cell cycle, for the initiation of the growth. Alright, so the lag phase, the length of the lag phase depends on these conditions I just talked about. So we will be moving to the kinetics of the batch culture. Okay, so the growth of the microbes is an autocatalytic process, that is the growth rate is proportional to the biomass. Thus microbial growth can be described as a proportionate increase in all of its cellular contents in the presence of appropriate medium and the cell conditions. All right. So how do you mathematically express the microbial growth? Here you can see an expression dx by dt is equals to mu x. Mathematically, how do you express the growth in a batch culture? A batch culture is a culture where all the nutrients, all the media is put in the container or the growth utensil, whatever you are taking, may it be a bioreactor or may it be conical flask. So all the media is taken together, the culture is inoculated once and then it is put into incubation. The cell will grow and it will follow the growth curve as I talked about recently. But in case of continuous, because the media and the fresh cells are continuously adding, it appears different than a batch culture. So here we are talking about the kinetics of batch culture specifically. So talking about coming back to the kinetics, all right. So mathematically, the growth in case of batch culture can be expressed at dx by dt is equals to mu x, where x is the concentration of microbial biomass, t is the time of growth in hours, and mu is the specific growth rate per hour, and the unit is per hour or per minute, whatever you can take. So if we integrate it, you can see dx by dt is equals to mu x. If we can rewrite this expression as dx is equals to mu x into dt, yeah. So if we rearrange this equation, this particular equation as dx is equals to mu x into dt, and then we integrate it. Okay, so do not be afraid, because we are talking about mathematics now, and it is a basic mathematics that you have learned in 9th and 10th, not even 11th, 12th. Okay, so it's a basic mathematics, and this is very, very needed to understand the kinetics of growth. And we are studying the kinetics of growth in microorganism, so that if you are working with these microorganisms for the production of any product in a large scale, you need to understand this mathematics or kinetics, because this will be used to scale up the overall process. Okay, coming back to it. So if we'll integrate it by time is equals to 0 and time is equals to t, and the concentration of cells as x naught and xt. What is x naught? Is the initial number of cells when the time is 0, and what is xt? Is the final number of cells or biomass when the time is t. So let's talk about it. What was the initial equation? dx is equals to mu x into dt. If we'll integrate it, we will be getting natural log of xt by xo is equals to mu t. If we'll take an anti-log, this particular equation after integrating becomes xt is equals to x naught e raised to power mu t, where x naught again is the original biomass concentration, xt is the biomass concentration after a time interval of t hours, and small e is the natural logarithmic base, where x naught is the original biomass concentration, xt is the biomass concentration after a time interval of t hours after the growth, and small e is the natural logarithmic base. What does it shows? You can calculate, if you have this, you can calculate the specific growth rate of the particular bacteria if you have the initial number of cells and the final number of cells and the number of hours that particular cells has grown. So this is the significance of this particular equation. Please remember this. Now, so this equation can be rewritten as this is xt is equals to x naught e raised to power mu t. If we take a log on both the sides, what will it become? Log of xt minus log of x naught is equals to mu t, or log xt is equals to log x naught plus mu t. After taking natural log, it will become what? 2.303 log xt is equals to 2.303 log x naught plus mu t. Again, it can be taken as log of xt is equals to log of x naught plus 2.303 mu t. Thus, if we plot log of xt on the y-axis versus time on the x-axis, results in a straight line with a slope equal to mu is equals to mu by 2.303. What does it mean? If we have log of xt, if we have log of x naught, if we plot that, if we have time, the slope can be calculated by this mu by 2.303. We can calculate the specific growth rate. We can calculate the specific growth rate for a particular growth rate curve by this equation or by this equation which I just talked, equation number 1. So it will look like this. If we plot log of x on the y-axis and time on the x-axis, it will give a straight line, because it will give you an exponential growth, and it will look like this, and the slope will give you mu by 2.303. Bacteria divides by binary fission, and the increase in the bacterial population density is given by geometric progression like this. Okay, so we are now talking about generation time. How you can calculate the generation time now. Okay, here we calculated by this equation in a batch culture. We got to understand how do you calculate the specific growth rate or mu. Now we will understand how will you calculate the doubling time or the generation time. So what is generation time? The time required. I will be revising the terminologies which are very important for growth curve and growth kinetics. All right. So what is generation time? The time required to double its number, it means bacterial number, is known as generation time, and it is given by the expression TD. TD is the time taken for an initial number of population N naught to get double, N becomes 2 N naught. Please understand. So generation time is given by the expression T subscript D, and what is that? The time required for the initial population to get double. So if the initial population was N naught, after doubling time it would be 2 N naught. So the final number of cells after the generation time becomes N is equals to 2 N naught. Alright. So talking about equation number 1, natural log of xt by x naught is equals to mu t. Alright. Now what you have? The initial number of cells and the final number of cells, because you are talking about doubling time. So you have now natural log of 2 N naught by N naught is equals to mu. T becomes TD. Why TD? Because we are talking about generation time. Okay. So the equation becomes mu TD is equals to natural log of 2, or TD becomes natural log of 2 by mu. What is natural log of 2? 0.69 by specific growth rate. Now we have just studied about two things. Okay, now if you have a batch culture growth curve, if you have the number of hours it has grown, if you have the initial number of cells, if you have the final number of cells, first you can calculate via equation number 1 the specific growth rate or mu. If you now, next thing that you can calculate is the doubling time or the generation time, because it is very important. So you can calculate using again the equation number 1 by substituting xt and x naught as 2 N naught and N naught, and from this equation you can calculate the generation time simply by the equation TD is equals to 0.69 by mu. Mu you have just now calculated. Okay, so using the growth kinetics equation you can calculate two very important terminologies or expressions, that is specific growth rate in per hour and the generation time in hours. The differences lie in the microorganism with respect to their growth and production of products. So when we talk about kinetics of growth curve, we not only talk about the growth, but we also talk about products. We also talk about substrate that it is using. All right. So therefore, to get the desired product, microorganisms are grown as batch, fed batch, or continuous culture. Batch culture or fed batch fermentations are common than the continuous fermentation. The mode of fermentation depends on the type of product being used. Why are we talking about this mathematical expression of growth kinetics and growth curve? Because ultimately what we are doing is, we are using this microorganism to make products. All right, we are using this microorganism to make products, and we want to scale up. All right, if you want to scale up you need mathematical expressions. All right, so the microorganism, depending on their growth and the production of products, they are grown in three ways: either as a batch culture or a fed batch culture or continuous culture. Here we are only talking about the batch culture as of now. So what is batch fermentation? Again, we will be talking in detail. Batch fermentation system is a closed culture system containing an initial amount of nutrients and involves number of biochemical processes. In batch culture, the cell properties such as size of the cell, nutrients, metabolic functions vary considerably during the various growth phases. All right, the typical growth profile is given in the figure. We have already studied this thing. The batch culture growth curve looks like this. You will not see that in fed batch, you will not see that in continuous culture. This growth curve is specifically seen only in batch growth. All right, so we have already talked about this growth curve. So talking about the kinetics of batch growth again. So if we talk about the equation, it is nutrients plus microbial cell is greater than the cell growth, energy and the reaction products. Consider the operation of the batch system container, which initially contains a known growth substrate concentration capital S, and the container is well mixed, and therefore the dissolved oxygen concentration or oxygen O2 does not becoming a limiting factor for microbial growth. Please pay attention. Now we are moving to the batch culture. We have talked about growth. We have talked about the mathematical expression to understand how to calculate the specific growth rate and the generation time. Now we are moving to the substrate utilization and product formation, because why you are doing the batch growth, you are doing it, you are utilizing the microorganism to finally produce some product. Okay. So when we start the batch system, initial growth concentration capital S is known, okay, and oxygen is not as a limiting factor. We are not talking oxygen as a limiting factor because it is very well mixed, and all the oxygen is mixed well in the batch system, okay, so it is not acting as a limiting factor. So initially a known concentration of viable microbial cell or inoculum capital X is added to the container, and with time growth substrate capital S is utilized for cell growth. Therefore, over time we observe decrease in the substrate concentration and corresponding increase in the number of microorganism or the biomass. I'll repeat. Once the batch culture has started, it has the known amount of substrate capital S, known amount of concentration of substrate capital S, and the known amount of viable or initial number of cells capital X, alright. As the growth progresses, और आप जब आपके पास एक डब्बा है जिसमें खाना है, ऑलराइट, तो आप अगर 3 घंटे हो और आपको भूख लग रही है और आप उसमें से खाना खा रहे हो, तो खाना आपका कम होगा, और क्योंकि आप कंटिन्यूसली खा रहे हो सकता है आपका वेट बढ़े. इन अ सिमिलर वे, व्हेन यू आर पुटिंग माइक्रो ऑर्गेनिज्म ऑफ नोन अमाउंट कैपिटल एक्स इन द बैच कल्चर, खाना खत्म होगा, so there would be a decrease in the substrate concentration with time, and it would be minus ds by dt because it is reducing, the substrate is reducing, and there would be increase in the biomass, that means plus dx by dt. So during the lag phase, dx by dt and ds by dt are essentially zero. Why? Because there is no biomass growth, as we talked about, because now you have the basics of lag phase, the growth curve, okay. So what I told, in the lag phase the microorganisms are adjusting, they do not start immediately growth, and the growth is very less, so the overall change in the biomass dx by dt is zero, and because they are not growing, obviously the substrate remains same, so there is no change in the substrate with respect to time, so ds by dt are also zero. But when the growth becomes exponential, however, as the exponential growth phase begins, it is possible to measure dx by dt and ds by dt values, which are very useful for defining the important microbial kinetic parameters. Using the corresponding observations of ds by dt, that is change in the substrate with respect to time, decrease in the substrate with respect to time, and dx by dt, which is increase in the biomass with respect to time, just after the onset of exponential growth phase. In here we will be talking about it in the forthcoming figures and equations. We can compute the yield coefficients as capital Y xs and the specific growth rate mu using the forthcoming equation. Yield coefficient matlab amount of biomass that is increasing with respect to the substrate concentration that you are giving. The yield coefficient is change in or increase in the biomass with respect to the amount of substrate concentration or change in the substrate concentration. You can see that mass of the new cells with respect to the mass of the substrate consumed. Please understand the yield of the biomass as dx by ds. It is not dx by dt. We are not calculating the biomass with respect to time. Please understand, we are calculating the yield of the biomass with respect to the khana the microorganism are eating. So it is given as dx by ds, that means mass of the new cells by mass of the substrate consumed. But how do you calculate the specific growth rate? Mu is equals to dx by x naught by dt, which is mass of the cell produced by original mass of the cells by time. and mu का क्या होता है, per unit time, you can see here. Okay, so using these kinetic parameter, you can calculate the yield of the biomass for the bacterial cell in a batch culture and the specific growth rate, and if you know the specific growth rate, you can easily calculate the doubling time. The yield coefficient, commonly referred as the substrate to biomass yield, is used to convert between the cell growth rate dx by dt and the substrate utilization rate ds by dt. The yield coefficient and the specific growth rate used to develop three types of microbial kinetics relationship: monod, first order reaction, and zero order kinetics. Consider an adaptation period of cells. I'm not talking about lag phase. Consider an adaptation period for the cells for the new environment with no immediate increase in the cell number. Dx by dt is 0, ds by dt is 0. Commercially, it is beneficial to reduce the lag phase length by using the suitable inoculum. If you are using the microorganism commercially for the production of any product, you need to reduce the lag phase. Okay, why? Because you need biomass. Okay, you need biomass. So if you are working on a commercial scale, you are scaling up, you need to reduce the lag phase for the synthesis of the new enzyme, ATP cofactor, ribozyme. Slight increase in the cell biomass and volume, prolonged by poor quality inoculum, as I told you, in terms of volume condition. Okay, you already know about the exponential phase. In this phase, the cell multiply rapidly. Dx by dt is changing, ds by dt is changing, as well as adjusted to the new environment. The growth is balanced, growth is maximum. Okay, so the growth is maximum specific growth rate. So the mu at exponential phase is mu max. Okay, and is independent of the substrate or nutrient concentration. So in exponential phase, mu, or the specific growth rate, is mu max and is independent of substrate or capital S. In the stationary phase of batch culture, after exponential phase, essential nutrients in the medium is used up and the organism build up to inhibitory level. Exponential growth ceases and the stationary phase is reached. In the stationary phase, there is no net increase or decrease in the cell numbers. So in the stationary phase, S is equals to 0, the substrate becomes 0, the accumulation of desired secondary metabolite, the growth rate becomes equal to death rate, and there is no net growth. Talking about death phase, if the incubation, if you continue to incubate the cell culture after the stationary phase, cell may remain alive or continue to metabolize, or they may die. Death phase, in some cases, death is accompanied by lysis of the cells. Rate of cell death generally slower than the exponential phase. Decline phase, the final stage of cell cultivation. Here the death rate follows the first order kinetics. dn by dt becomes n minus kd by n. Upon integration, it gives to the equation n is equals to ns e raised to power minus k dt, where ns is the cell concentration at the end of stationary phase, kd is the first order death rate constant. Thus in batch culture, the cell properties such as size, cells, internal nutrients vary considerably during the all growth phases. Now finally, moving to the Monod equation, the most widely used expression for describing specific growth rate as a function of substrate concentration is attributed to Monod. Monod equation is the growth rate is a hyperbolic function of the concentration of growth limiting nutrient, and the expression is mu is equals to mu max in bracket S by S plus Ks. Here is the Monod equation. You can calculate the mu max, you can calculate everything using, or Ks monodic constant, using this particular equation, where m is the maximum specific growth rate, S is the concentration of limiting substrate in mg per liter, and Ks is the half saturation constant or Monod constant. Monod equation has two limiting cases. First, if the substrate concentration is high, if S is very high, that means Ks dx by dt is equals to mu m into x. Under these conditions, the growth occurs at maximum growth rate. If there is low substrate concentration, the substrate concentration is very less in comparison to Ks, then dx by dt becomes mu m s x by Ks. This type of equation is typically found in batch flask system at the end of growth curve, as the substrate is nearly consumed. There are very advantages of batch system. There is low contamination, capital investment is less, wide varying products can be produced, and high conversion rate of raw materials. But there are again disadvantages: low productivity, increased focus on instrumentation, several subculture required, high cost for labor, and more susceptible for pathogenic microorganisms and toxins. But there are application of batch culture. Products involving low risk of contamination can be produced, production of small amount of product, employing proper product separation in batch and semi-continuous process. This is the summary of the equation that we have talked. Thank you very much.